Hello everyone, I'm AMMAJI DUPPADA, and in this session we are going to see the proofs against case 1 and case 2. We have covered already two problems. So we come to know that bluntly we should not follow how we are writing the complementary function. So we are seeing the proofs against it. Let me take case 1. We know that actually in the case 1, what is the proof we have written, like what is the complementary function we have written, like c1 into e to the power m1x if m1 is the root, c2 into e to the power m2x if m2 is the root, and so on. How we have written this, so that we will see now. Let us say the equation is this. So d by dx is an operator operating on y, minus m1 is operating on y is equal to 0 is the equation. Now d minus m1 is equal to 0 is the root, and complementary function we are writing like this. But how we have written, that is, see, if you see this equation, dy by dx minus m1y is equal to 0, it's a linear equation, which is satisfying the Leibniz linear equation, right? Leibniz linear equation. So dy by dx plus py is equal to q. Here p is minus m1, q is 0. So what is the solution actually from the Leibniz linear equation? Y into e to the power integration of p into dx is equal to integration of q into e power integration of p into dx. So y into e to the power p means what? Minus m1, right? So integration of minus m1 dx is equal to q is anyhow 0. So total thing here it will be 0. So y into some constant, let us say c1, it is 0 plus c1. So y into e to the power minus m1x is equal to c1. So what is the output? Y is equal to c1 into e to the power minus 1 minus m1x. If you bring this side, e to the power m1x you will get. That's it. If it is one root, you are getting like this, c1 into e to the power m1x. If there are two roots, like let us say d minus m1 into d minus m2 and so on, d minus mn operating on y is equal to 0 if you come across. So all are factors. I told you this is linear and each one is a factor. So all sums you can write output as a complementary function is equal to c1 into e power m1x plus c2 into e power m2x and so on, cn into e to the power mnx. This is the proof against case 1. Now we will see if the roots are repeated, how we are writing complementary function. So that is called case 2. So case 2 proof, if roots are repeated, we write simply like this actually. Cf is equal to, we are writing like this, right? C1x plus C2. If two roots are repeated, if three roots are repeated, C1x square plus C2x plus C3. But in this case only two roots I am taking. So C1x plus C2 into e to the power m1x. Like this we are writing. How we are writing this one? So now we will see. We have already seen d minus m1 operating on y. What is the solution we got? Let us say z. So that solution is equal to, already we have seen in the beginning case, how much? C1 into e to the power m1x. C1 into e to the power m1x. So I am taking directly C1 into e to the power m1x. So d operating on y, what is called dy over dx minus m1 into y is equal to how much? C1 into e to the power m1x. Now see, this is also satisfying linear Leibniz formula. What is that? Dy by dx plus py is equal to q. So what is the solution? If it is a satisfying linear Leibniz equation, solution is y into e to the power integration of pdx is equal to integration of q into e to the power integration of p into dx. So from this, now I'm directly writing y into e power integration of p, how much? Minus m1 dx is equal to integration of q, how much? Q is this, right? C1 into e to the power m1x into e to the power p dx minus 1 dx plus some constant C2. Now, y into e to the power minus m1x is equal to integration of C1 anyhow constant, I am taking this outside, e to the power m1x, e to the power minus m1x you will get here from this plus C2 dx. So e to the power m1x, e to the power minus m1x, e power 0, nothing but 1. C1 into integration of dx. So C1x plus C2 you are getting. Left hand side e power minus m1x. Finally, you are getting y as e power m1x. I am taking that side. C1x plus C2 into e to the power m1x. This is the way how this C1x plus C2 comes in the case 2. If three roots are repeated, let us say, what is the complementary function? C1x square plus C2x plus C3 into e power m1x. If roots are repeated three times. If it is four times, like that, simply it will increase C1x cube, C2x square plus C3x plus C4. But remember how many roots are there or how many eigenvalues you got in the equation. That many number of arbitrary constants should come in the final equation. Nothing but output or response or complementary function. So this is the way we need to understand proofs. Like when you understand proof against each case, automatically you don't need to remember or by heart something like bluntly formulas like this. So this is the way proofs will come across in the mathematics. Now case 1, case 2, we have done two problems and we have seen how the proofs against each one. Now we will solve the problems under case 3 and case 4 in the next session. Thank you all for watching this video.